Hi all, welcome to this, the third and final video in our series looking at the hydrosphere. Now in today's video we're going to be looking at hydrographs. Now this is what a hydrograph is. It looks really complicated. We've got a graph here with three different line graphs on it. There's a bar graph in there. I've got a whole bunch of different labels. And what is this doing? What is it showing us? Now fundamentally a hydrograph shows us what happens when we've got a storm or a large precipitation event and how that has an impact on an individual drainage basin. Now the first thing that I want to do today is we're going to go through each of the different component parts of a hydrograph and have a look at what they are. Then we're going to look at how we actually analyse hydrographs and what kinds of things are we expected to be able to see in this kind of graph. Now the first thing that we've got is we've got precipitation, we've got rainfall, and we display that as a bar graph at the side and we measure it in millimetres. It's fairly straightforward. Now sometimes you need to look really carefully at these to get the timings, because the 0 is the very start of the rainfall, and then you can see here at around about 4 hours in we started to have precipitation. Around about 6 we've got a max, 8 it starts to tail off, and by 12 the rainstorm has stopped. What's the next thing that's going to happen? Well, we're going to look at discharge. So this is how the discharge in the river itself has changed with time. And we measure this in cumecs or cubic metres per second as the water is travelling through the river system. Now with this, we split this line up into a couple of different little sections. So first we've got the rising limb. So this shows us what happens to the discharge as we add that precipitation, as we add that effectively flood water into the system. It goes up to a point we call peak flow. Now peak flow, very simply, is when the river reaches its peak or its maximum discharge. We then add in a recession limb, or sometimes you'll see it referred to as a falling limb, and this is where the flood water starts to leave the system and the river level returns to normal. Now we've got a point between this, we've got basin lag time. Now all this means is that the time difference between when we had maximum precipitation and when we had maximum discharge or peak flow. And it's the time difference between these two things. We add into this, we've got base flow. So base flow is just telling us if we didn't have this rainstorm at all, what would the normal river discharge have looked like? Then we add in through flow and overland flow. Now, overland flow plus through flow equals storm flow. Now, what are those two things? What is through flow? What is overland flow? Now, overland flow is the volume of water that hits the river straight from surface runoff. So material that hits, anywhere on the land surface and just goes straight across the land surface into the river. Whereas through flow is water that hits the surface, infiltrates maybe a little bit, penetrates the ground a little, and then makes its way into the river. And if we add both of these together, we get storm flow. And then you get this complete hydrograph, which is, hopefully you now maybe understand the component parts a little bit better. But the question now arises, what are you expected to do with this? Now, yes, okay, very possibly, I'm not entirely sure the SQ ever would, but they could theoretically ask you to draw one of these. I've never seen it before. But it could potentially happen. But what's a lot more common is they look for you to analyse one. They look for you to look at a storm hydrograph and to tell us things about the drainage basin that hydrograph exists in. And there's different things that we need to think about, and this is what we're going to look at for the remainder of the video today. Now, before we go into any of this, you need to remember, if you're ever asked to analyse a storm hydrograph, there are some things that you are expected to talk about. We're looking for you to discuss the rising limb, the recession limb, lag time or basin lag time, how intense the rainfall is, how long it occurs over, what is peak flow as compared to base flow, and how long does it take to get back to base flow from peak flow, what is that recovery rate. And I say there's a variety of different things that we look at to get you here. So we've got the area and shape of the basin, the different rock types that we've got in the basin, what slopes do we have around the basin, what is the soil type, what is the drainage density, how do we use the land, what is the climate like, and tidally, what are our conditions. So there's a lot for us to get through, So let's crack on. Now, there is a huge amount of information in these slides. I will talk through it, but obviously feel free to pause and read stuff and all the rest of it. Now, the area of a basin, if we look at really, really large basins, they're just bigger. They've got a bigger chance of gathering in more precipitation, so they can get more runoff. However, this also means that lag time is going to be longer because the water has to travel further in order to make it from the outside edges of the basin into the river channel in the middle. A kind of slightly similar idea with shape. With shape, we more look at elongate basins as compared to circular ones. Now, if a basin is more elongated, you're going to find that its lag time is greater because, again, the water takes longer to get from the sides of the river, the sides of the basin, sorry, into the river. Now, rock type, we've got two basic things we look at. We look at permeability. How easy is it for water to penetrate the rock? So if a rock is very permeable, it's something like limestone, for instance, where there's lots of cracks and joints in the rock. It means that the water gets through it very, very quickly. You get rapid infiltration and very, very little overland flow. Now what this means is that lag time is going to increase because it's going to take the water longer to travel through the rock than it would for it to travel across the top of it. Now that also gives us a shallower rising limb. And it also means that our peak flow will be smaller because this water is going to take longer to get into it, so it's going to enter the river system over a longer period of time. If it's impermeable, we're looking at the exact opposite. Water is going to hit the river, and it's going to hit the rocks, going to hit the sides of the basin, and it's going to flow over the top and straight into the river. It's going to get in there really, really quickly, so our rising limb is going to be steep, our basin lag time is going to be short, and our peak flow is going to be higher because more water is getting straight into that river all at the one time. If we think about slope, now slope, to be really honest, is very straightforward. If you've got really steep slopes, water flows down those steep slopes faster, so you've got a shorter lag time and a steeper rising limb. The opposite is also true. If you've got a very shallow rising limb and a very long lag time, it might well be that you're in quite a flat drainage basin. Soil type is kind of similar to the rock type that we were talking about a moment ago. If you've got really, really thick soils, you get a lot of infiltration, which is going to slow down the rate that the water can make it into the river, increase lag time, etc. However, if you've got, regardless of how thick it is, if you've got a very impermeable or not a very porous soil, and these are a couple of terms in here, so if something's impermeable, it stops water getting in, entirely. If it's non-porous or imporous, it's more or less the same thing. It operates mechanically in a slightly different way, but for our purposes, we can consider the two roughly equivalent. But if you've got something like a clay soil, it will act as if it's impermeable, and that will reduce that basin lag time, and it will steepen up that rising limb. Drainage density, this is really pretty straightforward. The higher your drainage density, the faster overland flow you have. And again, the faster overland flow is, the faster water gets into the river system, the steeper the rising limb, the shorter the basin lag time, and the higher the peak flow. Now, land use. We've got a little bit on land use to consider. Realistically, we're looking at the difference between urbanised land and arable land. And for the concept of this, arable land is really just any land that is either being farmed or has been left in a kind of rural state. So we've got basically not tarmac and buildings. If we've got an urban area, lots of concrete, lots of tarmac, huge numbers of impermeable surfaces, that's going to give us a really steep rising limb, a really short basin lag time. We compound that by adding in things like drains that we have that mean that we'll get water getting through this system even faster. You think literally, what is a storm drain designed to do? It is designed to move water through an area as efficiently as possible. So that's going to increase that rising limb and make that lag time even shorter again. Also going to increase peak flow in the river that it eventually empties out into. Now normally, arable land, is very, very good at intercepting rainwater, and reducing the volume of arable land that we have available increases flood hazards because we don't have that interception of water by trees, by grass, by the soil. We also don't have the soil as a store of water, so that's going to mean that it gets into the river systems even faster, and it increases flood hazards. Something we're trying to do to remedy this is afforestation. Now, you may have heard of this process before, but simply put, it is replanting forested areas or areas that have been deforested. We seek to replant them. Now, this is very, very positive in terms of stopping flooding, because forests create a huge amount of potential for interception and transpiration, and that means that our rising limb is going to be shallower, our lag time is going to be longer, and our peak flow is going to be less. And again, very, very important. If we can do that, it means when we think about the river itself, less water gets in all at once. The same overall volume of water is going to travel through that river system, but it's going to do it more slowly, so the risks associated with flooding are smaller. If you look here through this, and just to give you a little comparator, so we've got a given rainstorm here, and if we've got a wooded rural area, our lag time is much, much longer, our rising limb much, much shallower, our peak flow much, much shorter, and our recovery rate, again, it is going to take longer for the system to recover as well. If we've got an urbanised area, our rising limb much, much steeper, peak flow much, much higher, lag time much, much shorter, and our recovery or recession limb is similarly very, very steep. And again, this is the kind of thing that you'd be asked to talk about in the exam. Now, last couple of bits to throw in, climate and tidal controls. If you've got high spring tides, now this can block the normal exit for water. So this is very similar to what you sometimes get in Glen Rosa. So if you've got a very, very high tide, water can't empty out of the river system because you've got the tide is like blocking the end and keeping it in. So that means that your recovery rate is going to be enhanced. It's going to take longer. Precipitation and temperature we're going to talk about in a moment. Because again, the thing about snowfall and whatnot, it can have a big, big impact. If you've got conventional rainfall in the summer onto hard ground, now that can produce really, really quick runoff. Because again, if you're in the middle of the summer and you've had a long period of warm, dry weather and you dry out the soil's not able to act as a store in the same way that it would normally. The water hits it, it doesn't infiltrate, it just bounces straight off and runs straight into the system. Equally, if you've got a long period of more gradual rainstorms, it means that it gives the ground a chance, it gives the soil a chance to gather up some moisture, become more like a sponge, and then you're going to have that gentler rising limb, and it's going to take longer for the same volume of water to pass through the system, which reduces flood risk. And this is just a repeat of the previous slide that I've included for no good reason. So we're going to wrap things up there. Now, this has obviously had a lot of information in this video, and we're going to spend 4 periods wrapping up hydrographs and then anything and everything else associated with Hydrosphere. So make sure that you've got some good notes on this. Obviously, you'll get these handouts, so you can make your own copies of hydrographs if you want, but you will get the ones that are included in this. And until next lesson, I'll see you guys later. Bye.